exponential function. So what we're kind of reviewing some algebra in 5.1 and 5.2. So we're reviewing how we can combine functions. And then in 5.2, inverses, inverses are very important. And one of the first important sort of relationship that really you need to understand inverses is to do is the exponential and logarithmic behaviors. So we start with the easiest of the two, which is the exponential function. Most kids, most people understand exponential function, exponential growth, exponential decay. All right, we're going to look at those and the natural number e, and then functions and applications that involve exponential e, the e function. Exponential growth, exponential decay. All right, so starting off, the exponential, just in general, an exponential function is of the form some constant times some a, which is again a variable, not a variable. A is a number. X is the variable. The exponential part comes from the fact that the variable part is in the exponent, right? A is raised to the variable x. A and c are constants, right? C cannot be 0, and a has to be positive, right? And not equal to 1. If it's 1, it's just a line, because anything raised to the 1 degree is that number. Right? So again, a is positive, not 1. C can be anything. The domain of exponential functions is everything. I plug anything I want into an exponent. Doesn't matter. Positive, negative, rational, irrational, roots. Anything I want can go into it. Right. Base A is what's called the growth factor. That's the number by which it's growing by over every given period of whatever x represents. All right, so x would be, because if you think about it, it's whatever it is you're multiplying out x times. The initial value, so when you see that in a problem, the initial value is always whatever that c is. So it would be the initial point 0c, right? If I take any base a and raise it to 0, well, anything raised to 0, use your calculator, take anything, raise it to the 0 power. It comes out 1. So the initial value, that c out front, will always come out when I plug 0 in. So the initial value is always, so the initial value, which is also the y-intercept, is that number out front. That number out front is my initial value, the y-intercept. A is always a positive to avoid imaginary numbers such as negative 5 raised to the 1/2 or 1/4 or something like that. Alright, so the difference between, just so you kind of understand it, exponential, because we talk about exponential growth, things are growing exponentially. Alright, so just to kind of understand the difference between a linear case, which is constant, and an exponential case, which grows faster as you move down the line. Alright, so the first example is your exponential function. Alright, and we're growing by a factor of 2. Right, that's the 2 is my base, factor of 2. So if you look at it, right, every time x goes up by 1, my function goes up by times 2, by a factor of 2. Right? Factor means what we multiply by, a factor of 2. That's a time symbol, multiply, right? I go from 1/2 to 1 to 2 to 4 to 8 to 16. So it grows rapidly. The next one would be 16 times, so 32 would be the next one. So it would be, again, well off my chart here. And so it's growing faster and faster and faster and faster and faster. It gets steeper and steeper and steeper as we move along. In a linear case, in a line where my growth constant, or my growth is constant, I grow by the exact same amount. I don't multiply. I grow by exactly the same. So in this case, we add whatever that value is, which would be my slope in this case. So we go up by 2 units every time. Right? It's constant. 2 units, 2 units, 2 unit, 2 unit increase. Where this one's not. It goes up by a factor of 2. I increased by 2, then I increased, so I increased by 2, then I increased by 4, then I increased by 8, then I increased by 16. Right, so again, it multiplies. It goes up faster and faster and faster and faster. And so that's the difference between exponential growth and linear growth, which is constant growth. Alright, so looking at, there are 2 types of exponential equations. I keep saying exponential growth, but there's actually 2 types. There's exponential growth and exponential decay, and that's what we're going to kind of get into in the next example. Alright, so I'm going to graph 2 functions with 2 different bases, but the bases are similar. Alright, so I've got my function y equals 3x, and I've got my function y equals 1/3 x. And so I picked the same sort of values, just slightly different. Actually, they're just the opposite of my 2. Alright, so start again. I'm just plugging them in. So remember, it's 3 raised to the negative 2, which would be 1 over 3 squared 1/9. That would be 3 raised to the negative 1, which would be 1 over 3. 3 raised to the 0 is 3. Or sorry, 3. 1. 1. 1. 3 raised to the 1 is 3. Then 9. 2.5 doesn't come out real pretty. It's about 15.5. And then 3 raised to the 3 is 27. Alright, so if I graph this, I draw a straight line. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. Alright, I need to go up a little higher. You have a grid on yours. It didn't cut and paste real nicely. It got really weird, so I had to redo mine. So again, there's mine. So if I graphed it, so I'm going to graph this in blue. So I start off at negative 2, which would be 1/9, so it'd be barely above the axes. It goes slightly higher at 1/3. Then I hit 1. And then at 1 I hit 3. And then at 3, and at 2 I hit 9. So 1, 2, so 3, 4, 5, 6, 7, 8, 9. I'm not going to mark off the 2.5. I'm going to go all the way up to 3. So 27 was way up here. So 3 goes all the way up to the top to 327. And so there is the function. And again, I could graph it. There we go. Alright, so there's y equals 3x. And I do have an asymptote here at y equals 0. If you notice, I plugged negative numbers in, but the negative numbers just give me fractions. 3 to any negative expression is just going to give me the fraction 1/3 raised to whatever x is. And so this is never 0. The fractions keep getting smaller and smaller and smaller and approach 0, but they actually never, ever, ever get to 0. So they always stay positive. Alright, now the other one. So graph the... So remember what this really means. This really means 1/3, which I can rewrite if I want to. 3 raised to the negative x if I wanted to. And so what's going to happen here is this is going to be a decay model. Right, so I plug my values in. I plug negative 3 in. Well, the negatives are going to cancel out, leave me with a positive 27. You can plug this in your calculus, about 15.5. So it's going to come out 9, 3, 1. This is going to come out 1/3, and this is going to come out 1/9. And so it's the exact opposite. If I go over here to negative 3, it's a reflection. I start up here at negative 3, 27. And then I go negative 2, 9, 3, 1. And then I come down. And so again, it has this opposite. It's exactly the opposite. It goes through because it's reflected. Because in reality, that's really that function where I reflected it over the y-axis. And so the blue is the exponential growth. The red is the exponential decay. Neither one of them ever go negative. They always stay positive. Right? The green one, though, is coming down and approaching 0. The bigger I get, the closer to 0 I get. The blue one is doing the exact opposite. It's growing exponentially. And if you look at the numbers, that's what's happening, right? These are going up by bigger and bigger values. First I go up by 3, then 6, and then 6.5, and then between 9 and 27. Actually, we'll just do 9 and 27. 16, right? 3, 6, and 16. Or 18. 3, 6 by 3s. 3, 6, 18. And so there's the graphs of those two functions, right? Which leads us to the basic characteristics of exponential functions. All right, the basic characteristics of exponential functions depend on what that a value is. Right? If the a value is, and I put bigger than 0, it should be bigger than 1. Right? For some reason, again, like I said, I had a little trouble with this one transferring over. So it's sort of split into two sections. So if a is bigger than 1, so it's anything bigger than 1, 2, 2.5, 3, 3.5, 4, 5, anything bigger than 1, the function has this shape. It always goes through the point 0c, and it's the exponential growth case, right? And it doesn't ever cross the y equals 0. All right? If the a value, remember a has to be positive, if a value is between 1 and 0, so meaning it's a fraction, like 1/3, 1/4, 2/3, something along those lines, it's this shape, right? It's an exponential decay, and then some properties that go with it. So if I'm the growth case, right, as I plug in bigger values of x, my function gets bigger, and it gets bigger very fast. The opposite's happening over here. It's getting smaller, and it's getting smaller very fast. My function approaches 0 as I plug in big values, and it's getting closer and closer to 0 very, very, very fast. All right, the domain and ranges are both the same. Both of them, I can plug anything I want. Domain is negative infinity to infinity. Range for both of them is 0 to infinity, where I can't include 0 because it never actually hits the x-axis. It approaches it, but it never hits the x-axis. All right, and so the x-axis is the horizontal, and it's true for both cases. The x-axis is a horizontal asymptote for the growth case, and the x is a horizontal asymptote. It's just on opposite ends. If it's the growth case, it's on the negative infinity side where it approaches the 0. If it's the decay case, it's on the positive infinity side where it's approaching 0. The exponential growth is increasing everywhere. The exponential decay is decreasing everywhere. So those are my properties. And just look at a couple more examples. All right, so it's just a reminder. So these are just a couple of examples that I have graphed here. All right, when the graph is increasing, our a values are always, so here's examples. The bigger the a value, the faster it increases, right? So if I've got 1.3, it's a very slow increase. If I've got 1.7, it's a little bigger, and 2.5, it's much bigger. And again, the bigger that a, the faster it grows. All of them go through that 0.01, and all of them have the x-axis as an asymptote. The increasing, so that's the increasing, so this is the decreasing case, the decay case. All of my values are fractions between 1 and 0. Right? The bigger the fraction, this time the slower the decrease. So the smaller the fraction, the bigger the decrease. Right? 0.15 is smaller than 0.5. 0.5 is smaller than 0.7. And so its behavior is exact opposite. Again, all of them go through the 0.01, and all of them approach the y equals 0. So this would be exponential decay. Right? It's getting closer and closer. It never hits 0, but it gets closer and closer to 0. All right, so those are the properties of the exponential function that hopefully you're familiar with. All right, we'll stop there. We'll pick up the next set of notes in the next video.